北京太诚信 solemnly introduces the digital assembly line for heavy-duty main retarders, with the concept of creating zero-defect products, integrating information technology, automation, and digital technology, and managing the quality of the main retarder products throughout the entire assembly process. Comprehensively improve on-site management, production efficiency, and product quality. Based on process control digital technology, real-time data collection is performed for servo pressing, electric tightening, shim measurement and selection, torque monitoring, and backlash measurement, creating a data chain throughout the production line. The core control points include main bevel gear preload shim, imprint shim, differential head shaft shim, automatic measurement and selection of input shaft shim, control of axial clearance, control of gear contact area, and automatic adjustment of backlash. AGV transports and positions the material rack to the accumulation and discharge line. The robot automatically grasps the main and driven gears and brings them online. The empty rack is automatically rotated out, and the rack is automatically transported by AGV. The robot grasps the gearbox housing, and the equipment automatically detects the main reducer housing data, providing information for the measurement and selection of meshing print shims. The robot grasps the material, automatically applies pressure to the main gear bearing, performs dynamic detection, removes unqualified products, creates conditions for controlling the preload of the main gear bearing within a reasonable range, and improves the one-time pass rate of preload shim measurement and selection. Automatically measure the value dimension of the main gear shaft, providing data for the measurement of the inner bearing. The robotic arm automatically grasps the inner bearing from the tray, assembles it into the main gear, and the press automatically presses it into place. Automatically assemble the outer ring of the bearing and measure the W value. Combined press, electric cylinder movement, press head expansion and contraction, line body floating, pressing in the outer rings of two main gear bearings and the outer ring of the input shaft bearing of the middle bridge. The state of the main bevel gear assembly is assembled, and the preload shim of the main gear is dynamically measured when the rotational torque reaches the standard, avoiding the influence of bearing press deformation on shim measurement and effectively improving the one-time pass rate of shim selection. After the shim measurement and selection is completed, the press exits the main gear shaft, and the shim is manually replaced and the outer bearing inner ring is pressed in again. According to the product parameters, the main gear shaft is rotated under a fixed pressure to verify the torque of the main bevel gear bearing and determine whether it is qualified. The rear axle adopts a simulated flange, and the middle axle brakes with a cylindrical gear, automatically tightening the main gear nut and detecting the rotational torque of the main gear bearing. For middle axle products, a cylindrical gear reaction arm device is developed, and its angle can be automatically adjusted according to different products. Press the oil seal into the bearing housing and detect the perpendicularity of the oil seal and face relative to the center of the main gear online. Assemble the flange and pre-tighten the main gear nut. The gluing machine automatically traces the glue on the upper surface of the main reducer housing, and the image recognition checks the quality of the glue. Place the imprint shim, glue again, and the main bevel gear automatically enters the housing. The robotic arm automatically grabs the main cone and quickly assembles and presses it into the main reducer shell. The robotic arm automatically inserts the connecting bolts to the bearing seat with pre-threaded nuts. The fully automatic tightening machine automatically navigates coordinates and tightens all bearing seat bolts to achieve the torque and angle values set by the process. The equipment automatically alerts in case of tightening failures. The truss robotic arm flips the main cone assembly 180 degrees and transfers it to the accompanying tray on line 03. The robot grabs the differential housing and places it on the rotating table. Workers assemble the planetary half-shaft assembly on the rotating table. The robot then assembles the differential housing and brings the differential assembly online. Under actual assembly conditions, the system dynamically detects the backlash between the left and right half-shaft gears and planetary gears, measures and selects the appropriate shims for the left and right half-shafts, and verifies their qualification. Automatically rotates and tightens all differential housing bolts to the torque set by the process. The equipment automatically assembles the differential and presses the driven gear into place. Automatically rotates and tightens all driven gear bolts to the torque set by the process. The robotic arm automatically grabs bearings from the tray, and the pressing machine presses the differential bearing inner rings into place. Automatically detects the end face runout of the driven gear under constant pressure. The equipment automatically adjusts the expansion of the differential bearings, automatically adjusts and controls the backlash between the main and driven gears, and verifies the rotation torque of the main reducer assembly. Two devices are arranged in parallel, working independently, and do not affect the subsequent tray circulation during operation. automatically drive the rotation of the main reducer assembly, automatically runs in, and automatically takes pictures and stores them at the convex and concave surfaces of the meshing contact area at the driven gear. The main reducer assembly is driven to rotate, detecting torque, collecting vibration signals from the main and driven gears, calculating peak factors, and determining the quality of the assembly. Automatically measures the height h from the outer ring and face of the input shaft bearing to the mating surface on the main reducer shell. The robot grabs the bearing seat and places it on a dual station device. On the measuring table, it measures the depth of the bearing seat bore, installs the input shaft shim, and presses the bearing outer ring. The equipment automatically compresses the bolt hole position of the input bearing seat, detects the axial clearance of the input shaft, and determines whether the selection of the input shaft shim is qualified. The robot automatically tightens the input bearing seat bolts to the torque set by the process. Automatically tightens the slot nuts while controlling and detecting axial clearance until it is qualified. Visual recognition locates the notch position of the main gear nut, and the pressing head automatically changes position, servo turns, and automatically presses. The main reducer assembly is driven to rotate, detecting torque, collecting vibration signals from the main and driven gears and the input shaft assembly, calculating peak factors, and determining the quality of the assembly. A heavy-duty robot grabs the rear axle main reducer assembly for line transfer and unloading, and the finished product is automatically transported into the automatic material warehouse. Error-proof, utilizing mechanical, electrical, and sensing technologies to prevent misassembly and avoid safety and quality issues caused by human factors, providing strong support for production management. Standard part batch scanning to record production batches. Full correspondence between tooling, workpiece, and program to avoid model change errors. Photoelectric automatic identification of workpiece presence and workpiece arrival. Automatic identification of oil seal misassembly or leakage. Automatic counting of picked materials to prevent missing materials. Logical automatic judgment to establish data correlation. Bolt counting and mistightening error prevention. Pressure and displacement error prevention to prevent excessive looseness, tightness, or insufficient pressing. Accessing reducer shell, main gear, and inner bearing data to select and measure imprint shims. Establishing a connection between dynamic bearing data and shim selection, as well as connecting multiple stations for bearing detection, main gear shim selection, main cone pressure measurement, and nut tightening to strictly control the torque at the main cone. Standard part batch tracing. Differential housing scanning and main gear scanning. Main reducer housing scanning and gear scanning. RFID collects pallet data in real time, records, and uploads it. The sample quality data is automatically uploaded to the scanner management system. The digital twin system monitors equipment operating status, building up dynamic data analysis reports and various statistical charts, providing a data intelligence platform for constructing top-level products.